Welcome to the AI Checkpoints. Before we dive in, just a quick disclaimer. This content is generated by AI, so today we are taking a really deep dive into EmbeddingGemma. This is a brand new open embedding model from Google, and it's specifically designed to bring powerful AI capabilities directly onto your devices. Our mission here is to kind of unpack what this really means for developers, yeah, but also for the apps you use every day and maybe for the future of, private on-device AI. Okay, let's unpack this first bit. We're talking about embeddings. Now, for a lot of people that might sound pretty technical, right? A term you hear batted around a lot. What exactly are they? And why are they so important for AI understanding language?
Right. Yeah. Embedding sounds complex, but the core idea is actually pretty intuitive. Think of them as maybe like a universal translator for computers. They take human language, sentences, whole documents, whatever, and turn it into a language machines understand. Numbers,
Mm-hmm.
specifically a long list of numbers, a vector.
Okay, a vector, so just numbers.
Well, not just any numbers. They're very carefully calculated. The whole point is that these numbers capture the meaning, the semantic essence of the text. So if two pieces of text mean similar things, their number vectors will be, mathematically speaking, close together in this high-dimensional space.
Ah, I see. So it's about the relationships between the words and ideas, not just the words themselves.
Exactly. It's how machines get nuance, context, all those little things that make language so rich. It's absolutely fundamental for, well, any AI that needs to genuinely understand text. Google's own announcement really stresses how vital these are.
That makes a lot more sense. Okay, so you have these powerful meaning-capturing numbers,
hmm
embeddings, and they often get mentioned alongside RG pipelines, retrieval augmented generation. How do embeddings actually, slot into that whole RAG framework?
RE, yes, becomes super important. RE pipelines are, they're a real game changer for getting AI to give answers that are not just fluent, but actually relevant and grounded in specific information. You can basically think of it in two main steps. First, you've got the retrieval part. The system uses the user's input, their prompt, to intelligently pull out relevant bits of information from maybe a large database or set of documents. Then second, there's the generation stage. Here, a large language model, like Gemma or something similar, crafts an answer. But, and this is the crucial bit, it doesn't just make stuff up based on its general training. It uses the specific information it just retrieved.
So it's like giving the AI some notes to work from before it answers.
Precisely. And what's really fascinating, and where embeddings come in, is that the quality of that first step, the retrieval, is absolutely critical. Everything downstream depends on it. Embeddings are the engine for that retrieval.
How so?
Well, when you ask a question, the system first creates an embedding of your question. Then it compares that question embedding against the pre-calculated embeddings of all the documents it knows about. It's looking for the closest matches in meaning, not just keywords. It's like a super smart semantic search.
Right, okay. So it finds the documents whose meaning is closest to my query's meaning.
Exactly. Think about it. Maybe you need a carpenter. You've got damaged floorboards, right? If your embeddings aren't very good, maybe just vaguely search wood floor help. The system might pull up articles on different types of wood flooring or maybe DIY repair tips that aren't quite right. The generated answer might be totally unhelpful, maybe even nonsensical.
Yeah, that's useless if I just need a phone number.
Right. But with high-quality embeddings, like the kind EmbeddingGemma aims to provide, the system understands the intent behind wood floor help in the context of damage. It retrieves the most relevant snippets, maybe from local business listings or specific repair guides. Then the language model can generate a truly useful answer, maybe suggesting contacting a local carpenter specializing in floor repairs. That initial retrieval quality is everything.
Okay, got it. Good embeddings are the foundation for good RAG. So if that's the case, let's dive into EmbeddingGemma itself. What makes this particular model stand out? What are its key strengths?
Well, the headline feature really is its performance relative to its size. Google is calling it best in class. Specifically, it ranks highest among open, multilingual text embedding models that are under 500 million parameters, according to the MTEB benchmark.
MTB, massive text embedding benchmark.
That's the one. And MTB isn't just, one simple test. It's this really comprehensive benchmark. It tests embedding models across a whole range of different tasks: semantic similarity, classification, retrieval, clustering, and it does this in over 100 languages. So hitting the top spot there for a model of this size, that's a pretty big deal. It suggests really robust, reliable performance across the board.
And it's based on the Gemma 3 architecture.
Yes, built on Gemma 3. And importantly, it's trained on data covering those 100-plus languages, making it genuinely multilingual. And size-wise, we're talking small enough that with quantization we can get into the later, it can run using less than 200 millibit of RAM.
Wow, less than 200 millibit. That's tiny.
It really is.
Yeah.
Especially when you consider its performance is comparable to models that are almost twice its size. It's punching well above its weight class.
Okay, that is impressive. Top performance, small size, multilingual. Now, you mentioned flexibility and working offline. This sounds like where it gets really interesting for developers and maybe everyday users. What does flexibly work offline actually mean in practice?
It means it's really engineered from the get-go to run efficiently directly on your hardware, your phone, your laptop. No constant need to ping a cloud server. This offline by design idea is key. It's small, it's fast, it's efficient.
And flexible how?
One of the coolest aspects is the customizable output dimension. It uses something called Matryoshka Representation Learning. This lets developers choose the size of the embedding vector they need, the full 768 dimensions for maximum quality, or they can truncate it down to, say, 512, 256, or even 128 dimensions.
Truncate, like just chop off the end.
Sort of, yeah. Chopping off dimensions typically degrades quality, but Matryoshka learning trains it specifically so. Even the shorter versions retain a lot of the meaning. This gives developers this amazing dial to turn. They can trade off a bit of quality for significant gains in speed or reductions in memory and storage, depending on the device constraints. Plus, it has a 2000 token context window, which is pretty decent for processing on-device.
And it works well with other tools.
Oh, absolutely. Google's made a point of this. It's designed to work hand-in-glove with Gemma 3N, their on-device generative model. Together, they can unlock really powerful mobile RAG applications, sophisticated semantic search, all running locally. And importantly for adoption, it integrates easily with the tools developers are already using, things like sentence transformers, llama.cpp, MLX, llama, LangChain, Weaviate, Cloudflare, llama index. The list goes on.
So developers aren't starting from scratch. They can plug this into their existing workflows relatively easily.
Exactly. Lowering the barrier to entry is crucial for getting this kind of tech widely adopted.
It's still kind of amazing that you can get this level of performance in such a compact package. What's the engineering secret sauce here? How did they manage this efficiency?
It's a combination of smart architecture and clever training techniques. The model itself is about 308 million parameters total. That breaks down into roughly 100 million for the core model logic and about 200 million just for the embedding parameters themselves, which is already quite streamlined. But then you have techniques like that Matryoshka Representation Learning, MRL, we just talked about.
Right, the Russian doll thing.
Yeah. That nested structure is key for flexibility without needing multiple models. You train once, deploy flexibly. It's very efficient. You get the full 768 dimension vector for top quality when you need it, maybe on a more powerful laptop.
Yeah.
But for a mobile app where memory is tight, you just use the first 256 or 128 dimensions of that same vector, and it still works remarkably well.
That's really neat. And you mentioned speed, too.
Oh, yeah, it's fast. Google quotes inference times under 15 milliseconds for processing 256 input tokens on their EdgeTPU hardware. That's fast enough for real-time responses in apps. Think about features that react instantly as you type, that kind of thing.
And the low memory usage?
Yeah.
Less than 200 millibit.
That comes down to something called quantization-aware training, or QAT. Basically, during the training process, they simulate the effects of using lower precision numbers, like squishing the numbers down to take up less space in memory. The model learns to compensate for this potential loss of precision during training. So when you actually run the quantized model on a device, it uses way less RAM, down to that sub-200 millibit range, but it maintains most of its original quality.
So it's trained to be good even when it's compressed.
In a nutshell, yes. And if you connect this to the bigger picture, all these choices, the MRL, the QAT, the architecture, they're all laser-focused on making advanced AI practical and performant on the devices we all carry around, moving intelligence from the cloud right into your hand.
Okay, so bringing it all together, what does this actually mean for listeners, for the apps they might use? What new kinds of experiences does this offline by design approach really unlock?
I think the biggest implication, especially today, is privacy. That's huge, because EmbeddingGemma creates these meaning vectors, these embeddings, right there on your device. Your sensitive data doesn't necessarily have to leave your phone or laptop to be understood by an AI.
So my emails, my notes, my messages, they stay local.
Potentially, yes.
Yeah.
The processing happens locally.
Yeah.
Your information isn't being sent off to some distant server just for the AI to figure out what it means. That's a fundamental shift. Plus, small technical point, but it uses the same tokenizer as Gemma 3N. That just means less duplicated stuff in memory when you use them together in a RAG app, making the whole on-device system even leaner.
Okay, privacy is a massive benefit. What about actual use cases? What could this enable?
Well, imagine being able to do a unified search across everything on your device. Personal files, text messages, emails, calendar events, notifications all at once. Finding things based on meaning, not just keywords. And doing it instantly, even if you're offline.
Like a truly personal local search engine.
Exactly. Or think about personalized chatbots. You could have a chatbot trained on, say, your company's internal documentation or a specific industry's knowledge base running entirely offline on your laptop via RAG with Gemma 3N. Expert help anytime, anywhere. It could also get much better at understanding commands for mobile assistance, classifying what you're asking for, and triggering the right function call, making those interactions smoother.
And developers can tweak it further.
Yes, it can be fine-tuned. If you have a very specific domain, a niche task, or even a particular language focus, you can adapt EmbeddingGemma to perform even better on that specific data. There's actually a cool demo out there, built by Joshua from the Hugging Face team, that visualizes text embeddings in 3D space. And the neat part is, it runs entirely in your web browser using transformers.js, a great showcase of this on-device power.
Very cool. So developers now have this powerful new tool in EmbeddingGemma, but Google also has its big cloud-based embedding models, like the Gemini Embedding API. How does a developer choose? When is EmbeddingGemma the right call versus Gemini?
Yeah, that's a really important practical question. It really comes down to matching the tool to the job, right? Google's guidance seems pretty clear here. If your priority is on-device deployment, offline capability, maximum privacy, speed, and resource efficiency, think mobile apps, desktop tools, processing local data, anything where sending data to the cloud is undesirable or impossible, then EmbeddingGemma is purpose-built for that. It's the optimal choice.
Okay, on-device equals EmbeddingGemma.
Generally, yes. But if you're building large-scale server-side applications, maybe processing vast amounts of data in the cloud, and your absolute top priority is achieving the highest possible embedding quality and performance without the strict constraints of running on a user's device, then Google's state-of-the-art Gemini embedding model, accessed through the Gemini API, is likely still the better choice. It delivers peak performance when run on Google's infrastructure.
So it depends on where the AI needs to run and what the main constraints are, device resources versus needing absolute peak quality.
Exactly. Understand your deployment target and optimize accordingly.
And it sounds like Google has made it pretty easy for developers to actually get started with EmbeddingGemma if they decide it fits their needs.
They have, yeah. The model weights are readily available on standard platforms, Hugging Face, Kaggle, Google's own Vertex AI. So easy to download. They've also put out good documentation, guides for inference, guides for fine-tuning if you want to specialize it. And there's even a quick start ARGA example included in what they call the Gemma Cookbook, which should help people get up and running quickly building those retrieval-augmented applications.
And the integrations with existing tools we mentioned earlier.
Right. Support for things like transformers.js, for web-based on-device AI, MLX for Apple Silicon, llama.cpp for efficient CPU inference, llama for running models locally. It slots into the existing ecosystem. It means developers can leverage this powerful tech without having to completely retool their entire stack.
It really feels like they're trying to democratize this on-device capability.
That seems to be the goal. Put powerful private AI tools into the hands of more builders, which leads to maybe a provocative thought to leave folks with.
Oh.
Well, consider this. What kinds of entirely new applications might pop up when you have AI that's this capable, this intelligent, running fully on your own device, completely private, no internet needed? Think about truly personalized experiences, deeply integrated into your life, but always respecting your data boundary. Things that react in real time, right there in your hand. How might that shift from relying on the cloud for intelligence back to the device itself change our relationship with technology? Feels like we're just scratching the surface there.
That's a fascinating point. The potential for truly private, personalized AI assistants and tools, it's quite compelling. Well, that wraps up our deep dive into EmbeddingGemma. It certainly seems like a significant step for making powerful AI more accessible, private, and efficient, especially on the devices we use every day. A big move for developers and potentially for all of us down the line. Hit like and subscribe if you like the content. See you next time.